or less. Yes, thank you. So, I'm going to tell you a little story that comes out of a project that was done together with this Piero Manfredi, another Italian, that was aimed at understanding a little bit more about vaccination against varicella and its possible utility. And that is because there has been quite a lot written about models for varicella and vaccination against it. And there's still some debate surrounding whether it will be useful or not in the end, economically and otherwise. And it's mostly due to the fact that varicella itself is a nice little childhood disease, which means, however, that every year it must hit quite a lot of people. I mean, usually a birth cohort or something like that. But rather few severe cases, but a lot of work hours lost. And if the calculation had been only on that, I guess that depends on how you calculate work hours. It might either be good or bad to vaccinate against varicella. But varicella has one more feature, namely that once a person has had varicella, the virus hides in the dorsal ganglia somewhere and then stays there. And either it stays there until you die, or else until it comes out again in the shape of herpes zoster, which is a kind of, well, not really deadly disease, but certainly might be debilitating. It might cost a lot in treatment or consequences. So that's not so nice when it comes out. And the link with vaccination is that some people then think, with some data to support that thought, that the reason varicella can come out is that herpes zoster can come back, usually at the age of 50 or something like that, 50, 60, is that your immune defenses in some sense have gone down, and then these viruses can escape and come out again. And so it is thought that boosting your defenses against the virus might help keeping this zoster away or down. And this boosting can either be, it has been recently proposed, by another vaccination in adult age, but normally it should work through boosting by simply contacting people, children usually, who have the natural varicella, and that contact should boost your immune defenses without giving you the disease. And this boosting action is more or less a little bit supported by experimental data that show that if you effectively contact the virus again, certain indicators of immune defense go up, and so there seems to be some kind of boosting action going on. Now, if this thing really works that way, then vaccination would have a kind of perverse effect for one generation, in the sense that the vaccination would hopefully take away most of the varicella from children generations after some years, and then adults would not be boosted again, and they would be much more susceptible to getting herpes zoster, and you would have some kind of epidemic of herpes zoster in that whole generation which has had varicella as a child, and that would last for 40, 50 years until they all died away, and longer than that politicians don't think, so this would be an economical problem. Now, and that is the reason for debate about varicella vaccination. Does this effect exist, and how strong is it, and how much would it cost, etc.? Would it outweigh the benefit of gained working hours, etc.? And so the result is that in some places there is varicella vaccination of children in place, in other places not. Other places are still thinking about it, trying to see if data says something. But I think that the longest vaccination data that exists, which is from the United States, are usually considered not really conclusive in some sense. At least that's what my medical colleagues tell me. And so anyway, there's still room for some projects trying to work out better models for varicella spread and how these things work and how possibly the boosting could work. Now, the boosting mechanism is usually thought of as people have varicella, they go into a compartment where they are then immune to varicella itself, but might be boosted. If they are boosted, they usually go to a compartment called boosted individuals, are more protected against zoster than others, and then usually it is assumed that this immunity declines in some way. So maybe with a certain rate you go back to being zoster susceptible, or maybe you go to a third compartment being partially zoster susceptible or something like that, and then you can be boosted again, etc., until you die or get zoster. Usually you get it only once, this herpes zoster. But in this whole thing, there is some space for thinking about how does the re-exposure process look? I mean, what will be the features of this? How many times will you get boosted, at what ages, etc.? Because if you think of it deterministically, there's a steady flow of boosting force on everybody. But if you think about it stochastically, then it must be pointwise events when you meet somebody and get boosted. And then you can ask yourself, when are these events and how many are there of them, etc. And this is what this is about. So I've already told you all about this, that the interest is in this boosting effect. And of course, the thing that drives boosting is something very akin to what is usually called the force of infection of the disease. The force of infection of the disease is traditionally defined as the intensity with which a person who has not been exposed before will be exposed to the agent in such a way that he gets the disease, which means that he must be contacted by somebody who has the disease. But also the re-exposure follows the same mechanism. The already exposed person must be contacted by somebody who has the disease in an infective stage in order to get this possible boosting effect. And we'll discuss this later, whether the force of infection that is usually assumed to work on first infection, if it's a good measure of the exposure also for secondary exposures after the first infection. But essentially, since the force of infection is defined as probability of meeting an infective person in an efficient way, if you have not been exposed before, if that condition, having been exposed before or not, doesn't change your behavior, then the same function should work also for further contacts, since they would have worked for the first contact, if you forget about that. So we'll use the force of infection, at least temporarily, until science catches up with us, as a prototype for what kind of exposure you can have also after the first infection. But we'll discuss this a little bit. So you all know what the force of infection is. It's that thing that diminishes the susceptibles in an infection model, right? And it's usually something proportional to the number of infectives. Here you have beta. This is the typical force of infection in a simple SIR model. But if you think of it more stochastically, which I'm inclined to do now and then it works like from the individual point of view as in survival data analysis, that you have this individual and during his whole life he's exposed to this force of infection, and sooner or later he will succumb to this force of infection and get infected. And how long he will resist is given by a kind of survival function, his probability of not yet being infected after time t or at age t or something like that. And that all depends on the integrated force of infection up to that point. To make sense of force of infection and things, you must think a little bit about the population. The force of infection is something that, as R0, doesn't really exist because it's a hypothetical construct that is kind of well defined and stable only if the population is stable as such, or at least if the population changes don't affect the way people get infected. So usually the models that contain force of infection assume a stable demography. And in that case you can tie the force of infection at a certain age on a person with how many infected there are of different ages and some kind of here contact matrix between ages. That's the usual ingredients in an age structured model, assuming all the time that this thing is stable in time. And this will turn out to be important, not so much in itself, but for how you estimate the force of infection. Now, one would like to estimate the force of infection. And under the stability assumption, then you have kind of simple relations. And this is the standard way of trying to estimate the force of infection, is going through a seroprevalence study. because in the stable situation, if you find in a sample of people of a certain age that a certain proportion have had the disease before that, and you see that thanks to antibodies and things like that, and the others have not, then you have a measure of the proportion having survived the force of infection up to that age. And then that is analytically tied, this function S, those that have survived without infection up to age A, is tied to the force of infection by this simple relation. You just take the derivative of that exponential function. However, that expression, and what you do from a seroprevalence study is that you estimate this function S, or maybe 1 minus S, depending on what you like. And that is okay, because what you want to estimate is a kind of curve that rises. If you look at people who have had the disease, 1 minus S, then it will start at 0 at age 0, and then it rises. And for childhood disease, it's almost 90% by the age of 15, maybe. And then the last 10% will be filled out over many years of adult life. And usually the thing should probably stop at 97%, because some people will never have it, but very few. And that's kind of easy to estimate in various ways. But the problem is that for the force of infection, you have this expression, and that is a lousy expression from a statistical point of view, because the S curve is a little bit noisy because of sampling, and therefore estimating its derivative is not the easiest thing you can do. And furthermore, apart from having a bad estimate of the derivative numerically, here you divide by S, which is 1 minus that 95%, which is a very small number. So every variation in S prime will be kind of amplified by dividing by that small number. So statistically, that is a worthless expression for estimating the force of infection as such. And therefore, there are 2 or 3 ways to do it. One is some kind of, well, you can call it non-parametric. You, for instance, very classically assume a piecewise constant force of infection, and that gives some structure to the curve you fit to data, and then from that fit you see what these constants were on various time intervals, if you're happy about that. And usually then the intervals will be kind of small and nice for the childhood ages, so you distinguish low infectivity before the age of 5, high infectivity between 5 and 15, lower again, etc. And then you'll have a long stretch from 20 onwards, low infectivity. You can do something more nowadays if you like to have splines of various polynomial families adapted to the curve. And once you have adapted those, you can take the analytical derivative of whatever you have adapted, and so you have some measure of what the derivative is. You can also be parametric, in the sense that one often suspects that the force of infection looks a certain way. Usually it looks like this. It has a peak somewhere in the childhood ages, school ages, and then it goes down again, and that's it. And then one can take a parametric family that looks like that, and then adapt it to data. And then once again, once one has an analytic expression, you can derive that and see how the force of infection is once it has been adapted. There's a funnier way of doing it today. You might use a weight function, your adaptation, and that has become rather popular, well, especially since the polymod study. I guess you've all heard about the polymod study, trying to figure out at least how many contacts that could lead to infection there are between people of different ages. Since one measures the number of contacts, one then needs a multiplier to say how many of these transmit infection. So one will have at least one free parameter to multiply the polymod matrix with to get what would be called a wave matrix, who acquires infection from whom, or something like that. Or maybe more, 2 parameters or whatever for different age bands. And you can use that as a weighting function in your estimation of the force of infection, essentially by some long detour. If you put that matrix in with a certain value of these infectivity parameters, you can simulate a whole epidemic in some system of differential equations. And in those differential equations, you can see all important quantities like the S curve, how many people have been infected before a certain, at least when the equations have run to the stable state. the S-curve in the model, and you can compare it with the S-curve in your data. And you can then modify your one or two parameters until you think that they are one fits the other one very well, and then you decide on those parameters, and then you go back into the model and see how does the force of infection curve look, which is a quantity that also can be calculated, usually numerically in the curve. So you get an estimate of the force of infection from the model that, however, has been fitted on data on another quantity, namely the S-curve, the seroprevalence curve. And that thing will be weighted by how the model looks, that is proportional to, say, the polymorph matrix. So it's a kind of Bayesian thing without Bayes, that you have an a priori that says it should work according to this matrix, but let's see how much, in a sense. And why am I telling you all these things that you already know? Because it will turn out to be quite important how you estimate the force of infection. So now let's go to the subject proper, namely the re-exposure process. And let's decide, at least to start, with assuming that the force of infection for the disease is the same force that drives further contacts. And the only assumption that is essentially needed is this kind of forgetfulness of the past, that your probability of encountering infective individuals should be the same whether you have or not have been exposed before to the disease. And that might seem reasonable, at least for childhood diseases that you don't care very much about. I mean, of course, you could imagine that adults, knowing that they had the disease as children, go out and meet more children with disease, and or less. But let's assume for the moment that you can use this force of infection that you estimate for your first infection as a measure for further contacts. Then, yes?
Can I just ask, is that the symptoms appear quite a lot after you are infectious, right? So that would also speak against behavior changes. It's first in zoster and varicella. First you're infectious and then you get the rash, don't you?
You mean in varicella itself? Yeah. Yes, I mean your chances are quite good that you meet a child that is infectious without you knowing it.
Yeah, okay.
And that helps in the sense of forgetfulness.
Yeah.
Then your behavior will not change very much compared to what you would have done otherwise. Okay, so but let's now just assume this, that we can take this FY and see what effect that has on the process of contacts. Now, with this forgetfulness assumption, then essentially you have an intensity for encounters over life, and the most natural model for that is a Poisson process with a variable intensity, which is given by the intensity of encountering these contacts. And then maybe, if you feel that you must be precise, you also put in the fact that people will not live forever. There's a lifetime distribution that you must respect for people's lives. And that is usually called the killed Poisson process, just a nice name. But that's it. And that's a simple object from a probabilistic point of view. So you can, once you have decided to work in this killed Poisson process with a given intensity, you can write up most of the things that could be interesting about the re-exposure process. And for instance, you can start writing down, and everything works mathematically in the easiest possible of ways. I mean, since you have a lifetime distribution, you start by assuming that you know how long somebody will live, and then you have an ordinary Poisson variable over a certain age span. And so you know expected values and everything, and distributions for number of contacts for that age. And since you then assume that the age is not given but random, you simply average everything over the age distribution, which would be that thing. In various formulae you do this thing more or less correctly. And so you can write down the formula quite easily for, say, the expected number of lifetime contacts with the infectious agents. That would simply be more or less the expected value of the integrated intensity until you die. And you can write down various other things. The problem is now thinking about what kind of results would be fun to look at to understand how this contact process works. And there are some problems. For instance, so you might accept that some people will have 0, 1, 2, 3, 4, 5, etc. contacts with the disease, and then you might ask, okay, when do these happen? And there's no obvious easy answer when this happens, because when does the third contact happen? Well, it only happens for a subpopulation, those that have 3 contacts, not for the other 2. And then it depends if they have exactly 3 or more than 3 and the third, etc. So effectively, there's so much choice between interesting statistics that it's not clear what you want to look at. But as soon as you decide on something, you can look at it. I mean, how many lifetime contacts, what's the distribution of that? How many re-exposures do you get? But now you start saying, given that at least 1 exposure exists, otherwise you don't have re-exposures. So that's already a subpopulation. And things like this, how many re-exposures after a given age, etc. But then you have to condition on people who live at least to that age. So you always get results for subpopulation, have to think about what am I conditioning on. So you can write simple formula like how many re-exposure will there be for those who are at least infected, and you get nice little expressions like that.
This is decreasing in the probability that C is larger than or equal than 1.
Yes, so and that expresses the conditioning that re-exposures are only defined if you have at least 1 contact.
Okay.
So that is the denominator. Those that have at least 1 contact can have 0, 1, 2, 3 re-exposures, but you must be infected once to be re-exposed. So the relation is essentially that re-exposures equals contact minus 1, but it's not perfect, otherwise it would have contacts minus 1 only, because the fact that you have been infected and have at least 1 contact in probability will give you a slightly longer life than the average life, because you had at least that time, and so you probably have more contacts than on average if you didn't know that you had at least 1 and stuff like that. So small modifications occur because of these conditionings. This one is the one I like, because usually I thought of this talk with the title "The Last Contact." It sounds a little bit dramatic. This is the distribution of the age of the last exposure. Once again, it's defined only for people who have at least 1 exposure, otherwise you cannot have a last one. And it's kind of easy, because if you look at what that says, it says that to have your last exposure at a certain age A, you must have a contact then, which depends on the intensity, and then no further contacts until you die. And then you die after that age in which we are supposed to have your last contact. And the whole thing only for people who have at least 1 exposure, though. You cannot. So that's a funny expression, the distribution of the age of the last exposure. Now, how does this work out? So some data, and then thanks to a lot of studies, there are a lot of seroprevalence studies done, at least in Europe. The ESEN project has provided us with that for a lot of agents. And another Italian, Emanuele Del Fava, has worked on this problem of estimating the force of infection using various statistical methods. And in fact, he used 2 methods, among others, to estimate the force of infection for varicella in Italy on rather recent data. And one, as you see, is of the kind fitting some practical family of things to data. Fractional polynomial models are useful things, but they don't tell very much about the mechanism, but they can fit things well. And he fits that to the age-specific prevalence, and then you kind of derive these and you find what the force of infection must be. But he also did this fitting, as I told you, by using the polymod contact matrix, and found the best fit according to that matrix, which will look a little bit different. And here, I guess, we see what happens. So these are the estimated forces of infection according to the 2 estimation methods. And you see that they kind of agree. They have a very high peak somewhere in childhood here. And then they all go down, both go down. But the polymod one gives a further little bump. And this range here, which looks like 30 to 70, I don't know, is probably the fusion of being a parent and being a grandparent. Because the polymod matrices emphasize that most people only meet people of the same age, but you also meet your parents and grandparents, although to a lesser degree. So they emphasize these contacts. And that is probably emphasized here then, as a result. But one should remember that these things have been fitted to the seroprevalence data, and the fits are equally good. So from a point of view of fitting the original seroprevalence curve, both these models fit quite well, as you see essentially here, because the survival function is, let's see, yes, it's what I called S probably. People who have, or did I call it 1 minus S? One or the other, either this is S or 1 minus S. No, this is 1 minus S. S usually goes up if it's a seroprevalence curve, having had the infection before A. But you see that both these curves are very similar, and data probably looked more or less like that. So both these two estimates fit quite well to data. And in fact, they fit more or less equally well. But they look different if you look at how the forces of infection are. And why doesn't this bump matter? Because it happens so late that it only modifies a little bit the level here of what remains of probability of getting an infection further on in age.
So what's the fractional polynomial?
It's the light gray one.
So what does that mean? What does it mean for the, as opposed to the polynomial contract?
Well, the fractional polynomial is just interesting. I'm sorry I don't have data here, but
Like
data would have looked more or less like this, right? And the gray curve is only interested in looking more or less like that. So it took a shape that was close to data and looked like that.
Okay.
And if you derive that and do whatever you should, then you get this gray curve here. And you see that it is a little bit higher for young ages, and that compensates for it being a little bit lower here, so it gives more or less the kind of same total. But the big difference is that this thing that looks different here doesn't matter very much for how data looks, which is more or less that curve.
Does it look different in different European countries or regions of Italy?
For regions of Italy, we don't know. For European countries, the general level of the force of infection looks a little bit different. There are countries that seem to, for instance, Italy seems to have a little bit slow increase in several childhood diseases. You seem to get them a little bit later in Italy than in other countries where you get them quicker. But the general shape is the same of these estimates, because essentially all estimates of force of infection look like the gray curve normally for childhood diseases, with maybe different levels then, if you're quicker or not in the beginning. And if you force the polymorph structure on them, they will all have some small bump there, because you emphasize that there must be some contacts with these parents and grandparents, and you force it to be like that. But the levels might be a little bit different. Okay, so you take this now, these curves, and some statistics on how long people live, but it doesn't matter, it turns out, very much, because people essentially live long enough for things not to matter for anything about childhood diseases. And here you can see then some easy statistics, but the numbers are interesting as such. The expected number of contacts with the infectious agent varicella virus is essentially 3 or 3.5, and not more. That's the first row. Of which re-exposures would be this for those that have time, don't die early enough to have a re-exposure. And that means that one at least has to think that most people don't have that many re-exposures, according at least to the force of infection that we estimate from seroprevalence data. We'll be talking about this later on. Other things are, well, the variance is not very important. It's just to show that in theory the variance of C is larger than the expected value, because there's over-dispersion and distribution because of the variable life length. But the effect is very small, so it doesn't really matter if one thinks Poisson or over-dispersed Poisson. These are, however, well, the predictions of what is the age on average at the last exposure with the thing. And you see that the polymorph 1 has a later average age than the fractional polynomial one, which is quite early, 33 according to that model. And that is not so strange if you remember that the polymorph thing emphasized force of infection at later ages, and that is shown. But these numbers, I mean, average age at last exposure is probably not very informative, because if you think about the process in some more mechanistic way, then you're almost surely exposed to the thing when you're a child. That's the first one. Then there might be a re-exposure quite soon thereafter, because the force of infection is still high, but that doesn't really matter. It would still be some kind of childhood age. Then you'll probably have to wait until you become a parent or something to get another chance. And then you're about 30 something. And whether you get or not re-exposed then you'll have to wait until you're a grandparent, more or less. Well, a parent plus 10 years, because the child has to be at the age of getting varicella to expose you. I mean, if you become a parent at 30, then you'll be exposed around 40 or something like that, because the child will get his varicella at 10. And then you have to wait further on until you're something, maybe you get exposed as a grandparent when your grandchildren once again get the proper age, right? So in fact, the average 30 or something like that probably doesn't tell the whole story. There will be groups of people that have different ages at their exposures. And how that looks, it looks like this. This is the actual distribution, instead of just calculating the average value of the age at the last contact, the last exposure. And this is just to show that with the two different models, this is about distribution of the age at the first exposure, when you get your varicella. And both models agree that that thing almost certainly happens before you're 20, and with the peak at maybe 10 or something like that. And that is in accordance with science, I mean, about varicella. Most people get it in this childhood age. And you see that there's very little difference between the models. Once again, polymorph gives a little bit less probability to the young ages, and it gives a little bit more here for 40, which in a sense is realistic, because if you think about it, all of us know some adult that got varicella late. So there must be a little probability for having your first varicella when you're 30 or so. I checked it in the Italian Institute of Health, and at least 3 or 4 people I met said, oh yes, I got it at 30. It happens. There is a small probability of this, that you don't get it as a child, but you get it later.
It's funny that you say that, it's not the second time I hear that if you compare these, because the fractional polynomial is simple curve fitting, right?
Yes.
Nothing about mechanisms,
No.
nothing at all. It's simple. This is a curve that fits.
Mm-hmm.
Apparently, from the data, if you believe the data, there is something else going on in the latter part, right? It might not influence things a lot because it's very late.
If you look at this, the first infection, yes. But that's because you're forced to polymorph structure on it. You say there must be some extra contacts around the age of parenthood, because that's what the polymorph matrix says, right?
And also, so my question would be: so why do we concentrate on finding expressions that have sort of mechanistic understanding for a curve that looks like that, rather than take a curve-fitting approach with a fraction polynomial? Because there must be questions for which this makes a difference. Right?
I wouldn't mind if people always use the polymorph matrix for fitting models. It would get cited many times then. I'm there somewhere as the 15th name or something like that on the polymorph study. But no, I think it's kind of wise to use information you have about context structures in interpreting data, which is what happens when you do it this way. It might not be the only way. It might not. There are even choices when you say let's fit it with polymorph data, because polymorph study came out with several matrices, the close contacts and all contacts and household contacts, etc. And you could use different matrices then to give different weights to various things. And you can also say that the polymorph study presumably was not very precise in its estimate of childhood contacts, because at least for early ages one asked parents how many contacts children have and not the children themselves. And so there are many things that could be said. Well, maybe one would like some other data set, except and not polymorph as such. But using it as a kind of a priori is kind of natural, yes, compared to just saying let's take a family of polynomials and see if third degree will fit, something like that. And what is fun is that the difference in force of infection that you saw in previous thing, next to previous thing, which, well, is noticeable. Disappears when you look at first infection, of course, and that is what is meant by this thing, that the fit to date is equally good because it reflects first infection. But it becomes enormously amplified when you look at last infection, because then you have really this bimodal thing that some people only get in contact as a child and never more. There's a certain probability for that. And then there's a larger probability, however, that you'll have a second one at least, somewhere in this quite large age band, either as a parent or so. And within this group, there will probably be people who have also 2 or 3 contacts, or 4 contacts, or whatever, depending on the life histories. But that is all mixed up here, since this is about the last contact. And this thing might, of course, have to do with herpes zoster. Maybe that little group, which, depending on how you define it, maybe has probability 20-30%, are those who get herpes zoster at the end because they haven't been boosted later on in life. Or maybe not, we don't know, because very little is effectively known about what gives herpes zoster. I mean, it's...
So is there epidemiology that says, for example, that school teachers never get herpes zoster?
No, there are some studies. My colleagues right now in Italy are trying to collect all these things and also do this kind of epidemiological studies on herpes zoster patients, asking them, herpes zoster patients and a control group chosen decently similar, asking them what their occupations are, what their contacts, if they have children, grandchildren, contacts, whatever, trying to sort this out. There are apparently some studies, but nothing really big and nothing really systematic. My favorite was to do studies on nuns and monks in closure, for instance, to see what their herpes zoster is and stuff like that. But one might think of many kinds of natural experiments that have been done in this that could perhaps shed some light. But there must be something more than just the time from the last exposure, if there is this strong boosting effect, because also many persons feel that, just as with labial herpes or something like that, zoster is something that might come after shocks, when you have low immune defenses because of other treatments, cancer treatments, whatever. I mean, so there might be other reasons as well, apart from this waiting time from last exposure. So that's something to be investigated. But
sorry,
yes.
Is it possible that these other reasons are all that is about, instead of there's no boosting at all? Is there compelling evidence that there is some boosting, or is or can it be explained by other factors?
Not really, because the epidemiological study that tries to correlate, well, to start with, when they had varicella, but that's not very interesting because most people have it in childhood. But it's very difficult for people to say when was your last contact with an infected child. So it's there's no direct evidence. What has been seen is that if you subject people to exposure, then some antibodies and things will rise, maybe.
Okay.
But on the other hand, no medical person seems to be able to say exactly how you translate antibody titers to effective defense against anything. So there's supposed to be some kind of correlating marker to your ability to fend off viruses, but nobody knows exactly how it works. So no, there is no...
Not even the age distribution of zoster cases?
The age distribution is known from some studies, and one knows...
There's evidence that it's more than just shocks. If it was just shocks.
No, it's not only shocks. I mean, there are people who are shocked and don't get zoster. I mean, since everybody has had varicella,
Yep.
Everybody in theory here should be susceptible. And I think that about, if I remember correctly, a third of persons get herpes zoster before they die during lifetime. So it's quite a high, but you can also get it in a milder form. I mean, for some months you have some problems and then it disappears. The big cost comes from when the condition does not disappear or leaves nerve damage and things like that, and you go on having pain and stuff. There are various syndromes that are more expensive. No, not so much is known. I mean. And even this is interesting, because if one forgets now the reason for doing this and thinks as a statistician, The whole last part of the force of infection, because if you noticed, there were no confidence bands around these things. The last part of the force of infection is very badly estimated, because it has to do with the seroprevalence curve that has now arrived at 95% at 20-something years of age, and then goes on until the age of 50 or 60 when people tire of taking serum samples. And it just oscillates between 100% and 95%, and depending on the samples that you take at various ages. And of course, whatever increase there might be in this very tight range is very difficult to estimate well. So effectively, which one of these, where were they? Last time we saw them. I mean, does it go on increasing like the black one? Does it look like this? Should it have stabilized before? That is very imprecise. And effectively, it doesn't matter at all for the age of first infection, because everybody is already infected before. So what the force of infection does after age 50 is unimportant. But for this reconstruction, it is the important part, and we don't know very much about it. And maybe it can be remedied by further statistical studies on contacts between people at various ages and things like that. But I don't know, if we want to estimate that part, we'll have to be, because the problem is that that part is unimportant from the natural point of view. Since everybody has got infection before age of 50, nature doesn't care very much how much potential infectious contact there are after that, because they won't be effective. But if we suddenly, by vaccination, change things, this goes for most the rubella effects and whatever. If we change things by vaccination and shift the disease up to higher ages in some sense, although this is not a disease but re-exposure, then exactly the contact patterns at higher ages would be important. And we cannot really study them by natural means. We have to do something unnatural to figure out how they work. Okay, that was it. Do you think they will charge me for this?
Yeah, we take that out of the daily budget.
I'll, yes.
Do people with zoster provide boosting to other people?
They could. They could. There are apparently cases even where somebody with zoster has infected a child with varicella in this case. So the virus is kind of active for a while. And although it should reasonably be concentrated, since it comes out of a dorsal ganglion, the thing is usually concentrated in a kind of belt here with skin eruptions. But in theory, yes, I guess you could have virus on your hands and then touch your grandchild. And then. So cases have been known where people are getting infected with varicella from an older person having zoster.
I think it's a lot more difficult because chickenpox can be transmitted like it's an airborne disease.
Usually, yes, among children. So this is more difficult.
You're
And you
really
have
in
to.
close contact and touching. It doesn't like spread in the air, infecting on the wound. So it's a lot more rare because it's more difficult.
But it can happen.
Surely the thing to do would be to learn about transmitting contact patterns from other infections where you don't have this problem, where everybody over 50 is already immune. So, for example, flu would be an obvious one, I guess.
Yes.
So in the time one spends with people and the kind of contacts you have.
There are many situations where it would be fun to study. For instance, there are also diseases to which you presumably lose immunity, like pertussis, that is supposed to effectively act also at higher ages, although with less symptoms and less things like that. Yes, I mean, every possible study that can shed some light on how forces of infection should act at higher ages might be useful in this age where we tend to become interested in the elderly more than in the children, and where we know what happens. You could also do some more direct studies. I mean, when the polymod things were done more or less interviewing in households, right? And so if we found old people, then we found them in households, certainly. Recently, one of my colleagues said that he didn't believe that that was the important part. The important part among elderly people is in old people's homes, where they often live more closely and could have better infection probability. And then the question becomes, how many old people, what ages live in old people's homes? And that's very different in different countries. In some countries you have large quantities of old people living in old people's communities or homes or some kind of arrangement. In other countries everybody lives at home until they die. And so there are many different things that should be investigated. But it might be useful for other diseases than exactly this varicella thing to understand these contact patterns.
What would it take to transfer this into flu or pertussis?
To translate this into flu or... Well, the problem is that the estimation of force of infection is less straightforward with non-completely immunizing diseases. I mean, the whole theory about this thing is built on the fact that it happens once and you get this survival curve and you use that. If you don't know that, then you must know something good about how quickly things decline. I mean, how often you can get it again and things like that to explain the seroprevalence curve. And as far as I understand it, from disease to disease, that's rather unknown. Let's say pertussis is suspected to be a disease you can have several times in your life, but will your antibody response be the same, just as strong at every age? Will it not? Well, I don't know. I'm of the skeptical kind, so I usually believe that we don't know very much, in fact, about these things. But I believe it's more or less true that we don't really. One can, of course, put up models. I mean, this thing about, say, losing immunity of some kind and then getting boosted, so has been modeled at least in 2 or 3 different ways. If somebody is interested, these Italians that I did work with, they also wrote quite an interesting article here, this Uzzetta, etc., because they resurrected an old theory from Hope Simpson, which is a long time ago. He was of the idea that once you get boosted 3 times, then the immunity is complete thereafter, because your immunity kind of increases more than it decreases between things. But essentially 3 times. While other models just say that it's like an insurance process. I mean, the things go down and then you get some payment and then it goes down again and then you get a new payment. And then it goes down again with the same exponential speed over the time. There are several ways that it has been modeled, and nobody knows really which model is correct. But the models at the end give different predictions of problems. And that's what this article is about, that's different possible predictions on what can happen.
Has the vaccination been introduced in the States?
Yes, as far as I know, about 10, 12, 15 years ago, something.
15 years ago. Has anything been seen that might give?
There are some reports, but as far as I know, the epidemiological reports then on the incidence of zoster were that it seemed to go up a little bit in some places, but not in others.
You know what the uptake is?
The uptake is also very variable between states. And
Is that correlation between the two?
yes, of course, no. I don't know. I mean, what I remember is that, no, that thing wasn't very conclusive either. I mean, because you also expect a certain time delay, I mean, between these things. Let's say that you start vaccinating children and you go on for 15 years. Then you have, at the end, almost eliminated varicella in children. Not for the first 5 or 6 years, but after 12, 15 years, you know. But still, I mean, just 5 years ago, people were still exposed to children with varicella, so the non-exposure period hasn't been that long yet on most people. And this is hoping that you have, I mean, thinking that you have eradicated varicella by your vaccination. If it hasn't even been eradicated because they are still not at the correct level, then exposure is still going on, and so it's an incomplete experiment on absence of boosting. And then, I mean, it's a problem having to do with reality. Okay, you feel up to the weekend now? Thank you very much.